Okay, what's up, fourth hour? How we doing? Okay, hey, so I changed up the angle a little bit. I was trying to get rid of that little shiny spot since we hadn't had to deal with that since completely virtual instruction. So I just wanted to go over 4.1, which was the reading guide that you guys started before we left. And you guys completed that in class on that last day for me. What was it? The Friday and Tuesday. Okay, so Tuesday, Friday, meaning A and B day. Okay, so as we transition back into this, okay, I'll see you guys tomorrow, which obviously today is Monday. But hopefully this angle works pretty good. I stood behind the camera there and saw that it was a nice thing, I'm just kind of offset instead of straight on. It takes care of that glare that was showing up right here, okay? All right, so the objectives, this is gonna go directly in line with the outline PowerPoint that I gave you all a hard copy on the day I saw you, either it was Tuesday or Friday, okay? Because I knew probably, obviously, we'd be at home, and I gave that to you, so that way you can fill it in. If you lost it tomorrow, obviously, you can come up at any time tomorrow or Wednesday, which is study hall time, and pick up a new copy for you that you can do it, because it's 14 pages, and that's a lot of printer ink, so I have that, but all of you should have it, but if not, I can get you another, no problems, okay? So I'm just gonna, go slowly into this with the periodic table since I don't have you guys in front of me, all right? But a couple of things that we're gonna work on, talking about Dalton's atomic theory, and basically why it was more successful than Democritus, which was one of the first people to address atoms and motions and particles and all that. Talk about charges and mass and location, where they're at, and just compare and contrast Bohr's model, which basically what they were trying to do with these is figuring out the shape of how things work, okay? All right, so the bell ringer exercise was basically talking to you about when they first started looking at atoms is we knew roughly where the particles were and how they were aligned, but we couldn't see them. So a lot of it was guesstimates, all right? So what we know now, obviously, is a lot more in attention to detail because of technology, okay? But it goes all the way back to understanding basically atoms are required. We're talking centuries, hundreds of years ago, all right? So let's go all the way back to what is the idea of a term atom. Atom basically is the term that means unable to break or to be divided, okay? Dates all the way back to the Greek philosopher Democritus, who lived in the 4th century BC, long time ago, people, okay? And then it wasn't until John Dalton, around early 19th century, 1808, took up the simple idea that Democritus, Dalton proposed that atoms could not be divided, but Dalton was the first atomic theory with a scientific basis, meaning, you got to think about, they had great ideas in post-history type time, but there wasn't the data to back them up. So they could have been really off in left field with an idea or really close and parallel to beyond. In this particular case, unable to be divided, an atom at the time, as we know, we can split atoms and it gives us nuclear power and lots of release of energy. But in this particular case, atomic theory with the scientific basis, it was Dalton's first approach, okay? All right, so basically, what are atoms, okay? An atom is the smallest part of an element that still has the element's properties. So we're looking at the periodic table, okay? Atoms, when they talk about 1 unit or 1 mole of that element, they're basically talking about 1 atom, okay? So every little block or every little element, iron, mercury, lead, whatever it might be, is considered an atom as a unit of that element, okay? It maintains the properties of those elements, okay? Atoms are the building blocks of molecules, okay? Just kind of showing you here, water, H2O, basically, 1 hydrogen with 2 oxygens attached, obviously makes up over 70% of who we are, okay? Just a little simple analogy, something we're real familiar with, okay? All right, so basically, atoms are made up of protons, neutrons, and electrons, okay? 3 particles. We're going to talk a lot about those particles. Protons have a positive charge, neutrons, neutral, means neutral, and electrons are the negative charge, okay? A couple things you also know about where you find protons and neutrons and electrons, okay? The subatomic particles, guys and gals. So basically at the center of each atom is a nucleus. I think we all know that, but if we didn't, charge those brains on those typically like nucleus, the powerhouse, or the center, the hub of all energy and activity, okay? And the nucleus is a positive electrical charge because protons are all found in the nucleus, which has a positive charge, and the neutrons. And the neutrons have a neutral charge, so it doesn't do the old checks and balances, like it's not a negative to out of balance, so they don't carry a charge. So obviously protons is going to make the nucleus a positive charge, okay? So the nucleus is made up of protons, which is the particle, a positive charge, and neutrons, thus that. Or we also call that the atomic mass, or the atomic weight, protons plus neutrons, okay? So moving around in all these different orbits or shells or spheres, or they have lots of different names, okay? Or these clouds, these mysterious little things, are your electrons. And each one of those carries a negative charge, okay? Let's see if I can get the videos to work here for you. Oh, this doesn't look like they want to work for me. All right. So basically, what is an atom if continued? Okay, unreacted atoms have overall charges. Okay, so unreacted atoms have no overall charge. Okay, although atoms are made up of charged particles, they do not have an overall charge. Okay, so we're just talking about the atom in general. Okay, so protons and electrons equal each other. All right. So although atoms are made up of charged particles, they do not have an overall charge because you have equal a number of protons, which are pluses, and equal a number of electrons, which are minuses, so plus checks. And the neutrons don't carry any charge, so you have a zero, all right? Or they cancel each other out, and there's not an overall charge of an atom, okay? All right? So to the right, we show you basically helium. You know, like you suck out of balloons, you know, non-volatile stuff. It's showing you a helium atom is made up of 2 protons, so the red are the protons. 2 neutrons in there as well. You can see there's blue and blue there, okay? So those don't hold a charge, so there's a plus 2, you know, 2. And then there's 2 electrons running around out here. So you have plus plus and the negative negative gives you an overall of an atom of helium, no charge, okay? So it's neutral, all right? All right, whoops, back up one. So it was Bohr's model, this is the gentleman who came up with this, was comparing electrons to planets, okay? And they were trying to just start somewhere, okay? It was a good idea, but they think of like the rings of Saturn, okay? How the planets go around the sun. They were thinking, you know what? The electrons go around like orbits or planets around the solar system at the time, okay? And the same way in various different shells or orbits or clouds, okay? So it wasn't until early 20th century, 1913, this Danish scientist, Niels Bohr, okay, suggested, okay, hypothesized, he suggested that electrons in an atom move in set paths around the nucleus, much like the planets orbit the sun in our solar system. Okay, it was a good start. Okay, somebody had to do something. Wasn't spot on. You'll find out, but it was a good start. So in Bohr's model, electrons can only be certain energy levels. All right. So he was right on that. There's only so much. It's kind of like saying I can only put so many people in the front seat of the car before I have to spill over into the back seat. Or if I have a minivan with an extra seat in the back, you know, I can accommodate 2 in the front, 3 in the middle, 3 more in the back, like that. So that's what they're talking about, like seats or shells, energy levels can only hold so many electrons in the closest shells to the nucleus. And as you got farther out, or the bigger the element, okay, or the bigger the nucleus, right, the more neutrons that surrounded it, therefore you started getting more shells, okay? So, or he referred to them kind of like levels in an elevator, okay, or energy levels. So Bohr's model of electrons is illustrated on the following slide. So the thing that they came up with was an elevator, okay? And this is what this is supposed to show, like if this is the nucleus, and you have your protons and neutrons here, guys and gals, okay? So that first level or first floor could hold, could hold 2 electrons, okay? Not very many. So if it had more than 2, instead of them trying to cram into this floor, the elevator went up and they just spilled over into the next energy level, okay? And that could hold as many as 8. Okay, energy level, 8 electrons second. And if you had more than 10, okay, like 2 here, and they spilled over, and then 8 here, so that's 8 plus 2 is 10. If you had even more than that, the next energy level could hold 18, and so on and so on. So as the energy levels got more abundant, they could hold more electrons. So it wasn't like the electrons just disappeared or forced themselves into an area that wasn't placed. They just carried over into the next energy level that was present within that element, okay? So this was a nice start, but they were talking about energy levels, okay, of an atom like the floors of the building show. Electrons cannot be between floors. They go 2, then 8, 18, and they just keep on going up, okay? So understand that basic concept. All right. So electrons act electrons act more like waves, okay? So it wasn't until 1925 Bohr's model of atoms no longer explained electron behavior. Why? Well, think about it. Our technology was getting better, so they were able to build on Bohr's idea, okay? And they, like they said, they came up with things, they were more like waves or vibrating type strings in which they were attached, okay? So it wasn't that Bohr was completely wrong, but like I said, it was a good starting point. So basically then, 25 years, by 1925, which was, what did I say, 1908 or 1912, almost a couple decades later, the new model was proposed or hypothesized that they behave more like waves or vibrating strings or particles, okay? So an electron's exact location, and this is to this date, they can get a little better, but we don't know exactly where they are. We just got a rough idea where they're traveling in this path or this orbit, okay, or this shell, okay? Kind of like a racetrack. It's there. They're moving really, really fast, but we can't see them, okay? So it's impossible to determine both the exact location of an electron in an atom and the electron's speed, but we got an idea. We can hypothesize or formulate a equation, I guess you might want to say, to know roughly how fast it's going, and maybe they could get lucky, okay? So the best scientists can do is calculate, like I said, the chance of finding an electron in a specific place at a specific time in an atom, okay? But what they were able to tell us, okay, is how many were in each level, okay? So for all intrinsic purposes, we're just showing because we're just learning the basics, okay? But we know electrons exist in energy levels. We were right on that, so Bohr was right, but we made it a little more accurate as far as not knowing exactly where they are. But we do know that, let's take the first 4 energy levels, 2, 8, 18, 32, and so on. So as you see, as the circumference around the atom gets bigger, so does the element, okay? And that'll make sense the more we start learning more about the periodic table, like those 50 elements I gave you multiple weeks ago that we'll really start dabbling with now, since we're in unit chapter 4, which is dealing with atoms and periodic table, okay? So the number of filled electron levels, atom, it depends on the number of electrons that you have present in. Remember, electrons and protons, same number. So if I had an atomic number of 50 protons, because atomic number is also the protons, that means I'm also going to have 50 electrons. So then first 2 would go here, then 8 more here would be 10, and then 18 more, and so on. So you get the picture how I just keep adding them up, okay? And they just keep filling in, all right? Okay, so the one thing they were accurate about is the shapes. So, you got your X, Y, and Z axis. So on a 3-dimensional, it's like a circle, okay? So there's actually different types of orbits, what they call the S orbital and the P orbital. And, they don't really collaborate with the shape, but, they actually do. So the S orbital, because it's shaped like a sphere or a ball, so that's why they call it the S orbital. And the P orbital, okay, is more like a dumbbell, all right, or a figure 8, right? So they know if a certain energy level has a certain shape, that somewhere moving around in this level is those electrons at that different level. They just can't determine exactly where and when they're going to go by a certain point, but they know they're in there, okay? So the shape, S, and you got the P, which is like a dumbbell, or as you see here, a figure 8, okay? So the orbits in the region of the atom where there's high probability of finding them, so they'd be looking for in these shapes. But they can tell the shapes of those orbits, okay? So, important thing, you hear me talk a lot about this extra electrons, or specifically called valence electrons, okay? They're talking about the electrons in the element that are found in the outermost shell of that atom, okay? So determine the atom's chemical properties, right? That's what gives a chemical or an element its reactivity or its positive, negative charge, because one of the things you're going to really find out about chemistry is all about positive and negative, opposites attracting or filling or wanting, meaning if I have a +2 and I got a -2, they're going to be highly attracted to each other or things of that nature. So that's an important thing to remember. When you talk about valence electrons, they're talking about the extra electrons that spill over into the next energy level that are not filling it up, okay? And that'll make sense the more we talk about this, all right? All right, so valence electrons are the electrons in an atom, like I said, that participate in chemical bonding. So it's those extra ones that bonds sodium and chloride salt together. Okay, it's those valence electrons, the have and the have-nots. They say, oh, I like these. They come together and they form a nice stable bond, which we know what is salt. That's just one example of a compound. Okay, so valence electrons, a very important word to remember. Okay. All right. So simple to the point. Okay, that was objective number one. Didn't want to overdo it, but we talked about protons, neutrons, electrons. Valence electrons, a little bit of understanding the orbits, Democritus, Bohr's, and the new models, and the elevators, and so on. So we talked a little about 4.1. This will rekindle us, I get it. As far as that, and covering that part of the PowerPoint, okay? So that's good on that one. I'm going to do them in sections like this, not to overdo it, all right? Okay, so I will talk to you soon. Boom, 4.1 done.